So this year in geometry, you're going to find that a lot of the stuff that we talk about, you have learned in previous math classes. It's just that our focus is going to be a little bit different. It's like what I was referring to before about the idea of proof. But a lot of the geometry you already know, like all the stuff that is in 10 through 13, 14, all of the area formula and stuff that come after that, and circumference of a circle and perimeter. So much geometry you already know. So let's get down to the stuff, the geometry that's the focus of 10 through 13. So the first one, we're finding the value of x, and we have ourselves a triangle. This was referring to what's called the triangle sum theorem. Triangle sum theorem. Now, you may not have called it a theorem whenever you first learned it, but you've probably heard the word theorem associated with something called the Pythagorean theorem. A theorem in mathematics is a statement that we know is true because we've proved it with properties and definitions and postulates and possibly other theorems. It's been proven. And it goes like this. If I have myself a triangle, here, I'm going to start with something like a right triangle. And I know that one of these angles is a right angle right here. That one's 90 degrees. And remember that we usually represent that with a little box. And officially a red box. So what about the other two angles that are right here? Those other two angles have to add up to another 90 degrees because the total number of degrees is equal to 180 degrees. So this is 180 degrees for all of the interior angles. Interior as in, the ones that are on the inside. So just as a sample, this could be something like this, 45 and 45. If I look at the sum of this, 45 and 45, there's 90, and 90 plus the other 90 makes 180 degrees, for example. Here, let me give you another one. Now, I'm not saying that we always have to deal with 90 or right triangles. It's just that they're pretty easy, and there is a huge focus of them on geometry in high school. So again, I've got my 90-degree angle. Well, what are two other things that could add up to 90 so that the total of this is 180 degrees? How about 30 right here? And then 60 right here. Again, so there's tons of things that you can think of, but the idea with the interior angles of a triangle totals up to 180 degrees. Now, not to be too spoilerific, we're going to see some universes in which this thing is not true, that you don't get 180 degrees within your triangle. You get something more, get something less. That's one of the cool things that we're going to look at this year. Okay. Next on number 11. It's about the relationship between sides and angles within a triangle. And I can demonstrate that right here. So take a look at this. 45, 45, 90 within this triangle. So this is what is called an isosceles right triangle, if you remember that word isosceles. Isosceles just means that you have at least two sides which are congruent to each other. Now, let me ask you this question. What is the biggest side in this triangle? Well, most of us would go, hey, the biggest side is supposed to be the hypotenuse here. And the reason why it's the biggest side is because it's across from the biggest angle. And that's true for any angles. The bigger the angle, the bigger the side that's going to be directly across from it. And it also works with, let's say, the small angle. The small angle is going to be across from the smallest side. This is called the side angle inequality. And it goes something like this. Let's say that I have myself an angle like this. Now, I'm going to take the same size of segments roughly, and I'm just going to open this thing up just a little bit more. So let's pretend like these segments are the same size as those. Look how nice and wrinkly this one is. I don't know what's going on there. But now, I think most of us would agree that this angle here is smaller than the second angle. I'll number them off. This is number 1, and this one, that's number 2. I would say, this is the way that I write this, the measure of angle 1 is less than the measure of angle 2, right? Now look at the side. I haven't actually made it yet, so I'm just going to finish off the triangle like this. Look at this side compared to this one over here. I'll call this one an A, and I'll call this one a B. And I think we could easily verify, we could easily visualize the fact that A is going to be a smaller thing than B, right? So likewise, that A is going to be less than B because it's the side opposite from that. And that's what it's referring to. The bigger the angle, the bigger the side has to be to connect the endpoints of that angle, right? All right, next up on number 12, this is referring to what is called the triangle inequality. Super important theorem in mathematics. Triangle inequality. And the triangle inequality says that, you know what? Not every single set of numbers makes a triangle. And we might think that, if I just gave you any 3 numbers, let's say that I gave you the numbers 1 and 2 and 3, could I make a triangle with those 3 numbers? If I had segments that have each one of these things as their lengths, would that make a triangle? So I'm going to start with a 3. So if I start with this segment here being 3, notice that I could break this 3 up into 2 parts. I could break it up as this piece is 1, and the part that's left over here is 2. So doesn't that make basically my other 2 pieces, my other 2 numbers that I just kind of made up right here? Now the question is could I separate these 2 pieces where it's joined up right here at this point? Could I open this thing up in order to create a triangle? And the answer to that question is a big fat no. So for example, if I open this thing up, this segment here is still the number 1, and then this segment over here is still the number 2, and you can see that it would never ever close. This would always have a gap in it. And it gets even worse. Let's say instead that I had a 1, and a 3. So I still have the 3, but then let's do this thing again where I have here, this thing is the number 1, that little segment. And then I have the same kind of segment over here on the right-hand side. So another 1. And now, could I ever open these things up in order to make a triangle? Well, this one is even more obvious than the last one, that it's going to have a huge gap in between it. It's never going to close off to make a triangle. So how do I know when the 3 numbers of that are potentially the side lengths of a triangle actually work? Well, here's one that most people are familiar with, again, dealing with a right triangle, and that is 3 and 4 and 5. So I'm going to draw a 3, 4, 5. It's actually the side lengths of a right triangle here. So I'll put, there we go. This is a super famous right triangle, side lengths 3 and 4 and 5. And what makes this different from the other ones is the fact that if I were to take 2 of the sides, any 2 of the sides, and add them up, I'm going to get something that's bigger than the third side. And it goes like this. Let's say, for example, I do 3 plus 4. Add that up, that's 7, and 7 is definitely bigger than 5. Now, in practice, when I know all the numbers, the only ones you have to focus on are the 2 smaller ones, adding those 2 together in order to make sure that it's bigger than the third side. However, it's true for any 2 sides that I choose. For example, if I pick 5 plus 4, that's got to be bigger than 3. And that one should make sense because, look, 4 is already bigger than 3. So if I add 5 to it, it's going to be bigger as well. But then it also works with 3 plus 5. If I add those 2 together, 3 plus 5, that is, that's definitely bigger than 4, right? Well, because 5 is already bigger than 4. Let's take a look at that with the other two that I just demonstrated up here. Whereas you could write something like this. You could write 2 plus 3 is bigger than 1. Hey, yes, it works, right? Well, no, it doesn't work because there is one that you can select that the triangle inequality is false for. So that would be the numbers 1 plus 2. That's equal to 3. And 3 is definitely not greater than 3. It's equal to 3. So that's why it doesn't work. Okay, and then likewise, the one that's right here in the middle, I could do 1 plus 1, which is equal to 2, and 2, definitely not bigger than 3. That's a big fat no here. Even though I could pick 1 plus 3, which is equal to 4, which is bigger than 1, like any way that I arrange it always has to be true, and that's what the triangle inequality is all about. So speaking of the triangle inequality, where you add up any two sides of the triangle, it's got to be bigger than the third side. That's exactly what question number 13 is about as well. So you're actually finding, hey, if two of these sides, 5 and 12, are side lengths of a triangle, what could this last side possibly be? And you're writing this thing as a compound inequality. So not to give you the answer here, but just to remind you what compound inequality looks like, your answer is going to look like this. So usually compound inequalities, you have either ands or you have ors. They're separated by fanboys. Those are the two that we usually see in mathematics. Okay, so this one is going to be an and compound inequality. And inequalities go from smallest to biggest. And it's like this. As an example, I would have 3 is less than x, which is less than 7. And what it means is that x, whatever that value is, it lives in between 3 and 7. It's not the number 3 because there's no equal sign here. It's not the number 7, but it's anything in between there. So it could be 4, it could be 4.1, it could be pi, because pi lives within that little range. And you may remember in algebra writing domain and range in those kind of compound inequalities. So that's the kind of thing that we're looking for. And no, this is not necessarily the answer of this one. I just made up that inequality. All right, and then one last thing before we go, and that is on number 14, comparing units, feet, and feet squared. So what I want you to think of are not necessarily the fact that this is like squared as in feet times feet, which really is what it is. It's about dimensions of stuff. One dimensions versus two dimensions, and then you eventually learn about volume, which has 3 dimensions, and what these things are associated with, what kind of measurements. Feet measure one kind of thing that's different from what feet squared are supposed to be measuring. And then if you don't quite remember what those things are, all you have to do is start looking at the next set of problems, and maybe those will give you some hints as to where you're going to use feet differently from feet squared.